Our next speaker is Mohammad Abdul Aziz, and we're going to have to pass him the microphone, but he's going to tell us about a state space acyclicity property for exponentially tighter plan length bounds.
Hello, everybody. Today I'll be talking, as Aziz just said, about computing upper bounds on the lengths of plans. This is joint work with my PhD supervisors, Michael Norrish and Charles Gretton. I did this work when I was when I was still in Australia in ANU, but now I moved to Technical University of Munich, where I work in the chair of logic and verification as a postdoc. So today I'll be talking about the talk will be primarily in two parts. First, I'll be talking about two new algorithms to compute upper bounds on plan lengths. Secondly, I'll briefly talk about formally verifying those algorithms in an interactive theorem prover. So the outline of the talk is, first I will introduce what am I computing upper bounds on, and how am I computing those upper bounds, and what systems are we considering for upper bounding, what transition systems are we considering for upper bounding. The second thing I will be talking about the upper bounding algorithms in the literature and in the previous work in the literature. And the third thing is that I will be talking about our algorithms, and lastly I'll be talking about the formalization. Oh, sorry. Hello? Okay. So the systems that the systems for which we compute upper bounds we call propositionally factored transition systems, and those are basically systems where actions are pairs of partial states. So and the first member of the pair is a precondition of the action, and the second one is the effect. So for example, here action A has preconditions x false and y false and z true, and its effect is that it sets y to true. So a set of those actions forms a transition system, and it succinctly represents the state space, and it can be exponentially smaller than the state space. So in order for us to upper bound plan lengths, we compute upper bounds on topological properties of those state spaces. And by that I mean properties like the diameter of the state space or the recurrence diameter of the state space. And those properties are themselves upper bounds on the length of any optimal plan in terms of length that you can imagine. And the reason I'm doing that primarily is to guarantee the completeness of SAT-based planning and boundary model checking. Because, for example, those two methods, in order for them to be complete, you need to have a practically tight upper bound on the length of transition sequences that you need to consider in your search. So I'll very briefly define the diameter and the recurrence diameter. So the diameter is defined as the length of the longest, shortest transition sequence between any two states in the state space. Or so basically between every pair of states, you see what's the shortest action sequence, and you take the length of the longest one of those, and this is the diameter. So for example, for this clique, the diameter would be 1, because you can reach any state from any other state in one transition. The recurrence diameter, on the other hand, is the length of the longest simple path in the state space, or the longest transition sequence that doesn't pass any state more than once. So for the clique, the recurrence diameter here would be 3, because you can have 3 transitions without repeating any state. Like for example, the transition from here to there to there to there. So there are 3 transitions without repetitions. So the main challenge is that existing algorithms for computing those properties assume that you have the directed graph explicitly, and in order for one to use them to upper bound the state spaces of those factored systems, you would have to potentially construct an exponentially larger state space, and this will lead to an exponential blow in the complexity of computing both properties. So the solution or the approach that we took to circumvent this problem of exponential blow in the complexity is that we used compositional algorithms, where basically you compute upper bounds on abstractions and then compose the upper bounds for the abstractions to upper bound the concrete system's diameter. And the advantage of this approach is that abstractions upper bounds can be exponentially smaller than the concrete system. Sorry, abstraction state spaces can be exponentially smaller than the concrete system state space. But a problem with it is that you need. How do you know that composing abstractions upper bounds is actually a sound upper bound on the concrete system's upper bound? So a way to guarantee that the composition works is that you restrict your the systems that you consider to systems having a certain structure, like acyclicity in the state space or acyclicity in the dependencies, and prove that a certain compositional algorithm always works for systems that have this structure. So previous work on upper bounding, on compositional upper bounding, considered computing upper bounds on projections of the system, and those projections are computed by analyzing the. And this approach was independently invented in the verification community and in the AI community. And basically, so before I quickly describe the approach, I will just say what projection is, to those who don't know it, and what dependency is. So a projection of a system is an over-approximation that removes state variables from the system. So for example, in our example system, if we want to compute this projection on x and y, we would remove z from everywhere. So as you can see, z is gone from all the actions, and the state space collapses to a much smaller state space. And dependency dependency between variables or causality relation between variables is defined as follows. A variable is dependent on another if and only if the assignment of V2 if and only if a change in assignment of V2 can possibly change the assignment in V1 in the current state or in a future state. So in our example, we have variables x and y both dependent on z, because z is in preconditions of effects that influence x and y, but z is not dependent on anything because those are not in preconditions that influence z, and actually z doesn't change in the system. And the strongly connected components of this, we call this graph the dependency graph, and usually people usually people compute the strongly connected components of this graph for many purposes. So the main approach of projection upper bounding that exists in the literature is that you basically compute the strongly connected components of the dependency graph, and then compute projections on the strongly connected components, and then upper bound the diameter of each of those projections, and then upper bound the diameter of these projections by computing the recurrence diameter of the projections, and then compose the recurrence diameters of the projections to upper bound the concrete system's diameter. So another piece of previous work is a paper that I authored with Michael Norrish and Charles Gretton as well in 2015, where we improved the algorithm that was used to compose projections diameters, projection upper bounds, and the new algorithm that we constructed always computes tighter bounds. Like we experimentally showed that, and also we proved that it cannot be improved. And we also showed that instead of using projections recurrence diameters, you can use projections subless diameters, which can be exponentially smaller. So basically, to summarize, all the previous work was on using projections upper bounds to upper bound the system's diameter. So the first new algorithm that I'll be talking about today uses a new abstraction that I refer to as the snapshot, and it is computed based on state space acyclicity. So a snapshot is an under approximation of a system that's based on removing actions from the system versus state variables. Like for projection, removes state variables. This one removes actions. And it removes actions violating a given assignment. So for example, if you take the snapshot of the example system on the assignment z to true, you remove all the actions that operate when z is false. So you have lost, this clique is now a set of 4 singletons. So the main idea of this snapshotting algorithm is the following. It's in 4 steps. So the first step is that you find a projection of the system such that the projection has an acyclic state space. So for example, if we project our system on z, So we basically remove x and y, you have this state space, because that didn't change in the system that we had. And then for each of the states in the projections state space, you compute the snapshot of the given system. So here we're computing the snapshot of the given system on Z and Z bar, which are the two states in the cyclic state space of the projection. And then the third step is that you compute the diameter of the snapshots, of all the snapshots. So here we have the diameter of this snapshot is 3, and the diameter of that snapshot is 1. And the last step is that you compute the snapshot diameters. And the way, you compose the snapshot diameters. And the way you compose it is basically you label the acyclic projections state space. You label every state with the diameter of its corresponding snapshot, and then you compute the weightiest path in this directed graph where the weight of a path is equal to the weight of the vertices in that path. So for our example here, the upper bound would be the longest path in this graph, the weightiest path in this graph, which is just 3 because there are just 2 separate nodes. A challenge with this algorithm, though, is that the number of snapshots can be intractable. So a way to circumvent that, we devised another algorithm, which we refer to as a hybrid algorithm. And this algorithm interleaves projection and snapshotting. And basically, it reduces this, it circumvents this intractability by computing snapshots on projections of the system. So you don't have very big state spaces. And this hybrid algorithm basically does the following: you try to compute non-trivial projections, where basically which basically means if the dependency graph has more than one strongly connected component, you compute a projection-based bound. Otherwise, you do snapshotting. If none of the structures are existing, you just return the number of states. And I would like to note that whether in the projection or the snapshot, when you do projection or snapshotting, you actually invoke the same algorithm again on each of the abstractions. So this is a mutually recursive algorithm. So this algorithm actually computed bounds that are practically very useful. They're much tighter than the state of the art. And we combined the bounds computed here with Madagascar, the SAT planner by UC Rintanen, and it enabled Madagascar to prove unsolvability for 54 IPC unsolvable benchmarks, and also it helped Madagascar show 160 problems have plans, and it could, and though Madagascar couldn't show that it has plans, those benchmarks had plans with its default querying strategy. And it also helped us close some verification problems, like most notably the hotel key protocol problem from Daniel Jackson, 2006. So now we'll very briefly talk about the verification. So reasons to verify AI algorithms are, there are regular reasons to verify any algorithm where you want to catch subtle bugs in the algorithm, whether in the abstract or the implementation level, and also to gain deeper understanding of the underlying algorithms, which can help you improve them. Other reasons also is that the algorithms are getting very complicated, and the length of the publications is almost fixed. So this gives quite a room for obtaining reliability through verification. Because of the lack of time, I will go to the next one. So we used an interactive theorem prover to formally verify those algorithms, and by that I mean. So by an interactive theorem prover, I mean a system where you can formally define objects in a given type system. And in this system also you can formally state statements about the objects that you define in the type system, and most importantly, compose and check proofs about those objects. So basically it's a system where you can define things and formally prove facts about them. So the system that we use is Hall4, and it uses higher order logic. The most prominent feature of that logic is that it allows quantification over predicates and functions, and it has its architecture allows for very high reliability because it has a very small trusted code base. So the library size is 16,000. The proof scripts are 16,000 lines, including a lot of background theory, and it helps us find bugs in our work and as well as in previous literature work. So to conclude, we introduced one compositional algorithm based on a U abstraction, and another compositional algorithm that combines both approaches, the one based on the snapshotting and the other one, the previous one based on projections. And those bounds were used to actually practically solve problems by a SAT-based planner. And we formally verified all of that in interactive theorem prover. Thank you.
Questions?
So I like the idea of formally verifying your algorithms, but and I know you didn't have time to go into this in depth.
Yep.
But I'm a little perplexed about exactly what you used Hall to do. Did you use it to basically back up your proofs? Did you use it to basically auto-code your code? Can you say one or two more words about that?
Yeah. Okay. So the current state of the formalization is that we in Hall 4 we used we defined the algorithms abstractly. Okay. So we defined them abstractly in the sense that we're not referring to an implementation. We're just referring to an abstract definition of the algorithms, and we have proofs that those algorithms produce correct upper bounds, the abstract algorithms. But a next step for that is that we would refine those abstract definitions into an implementation, and this refinement also would be formally guaranteed to be correct because it will be done within the theorem prover. But we didn't do that yet. So does this answer your question?
No. I should probably read your paper before I ask again.
Okay.
So did you verify the proof generated by Hall? So,
Yeah.
So Hall outputs a proof, right?
Oh no. So it's an interactive theorem prover. So you probably guide. So what happens is that you guide it through the proof by relatively high level steps, and it generates intermediate steps.
All right.
And your high level steps and the intermediate steps are checked by proof checker, which is a part of Hall 4 as well, and this is trusted.
All right. But did you verify it manually after all the automated thing?
No, you cannot verify.
What level of verification or whatever?
So verify. So okay. So I'll ask you a question. You mean verify Hall 4 or verify our proofs?
Verify the whole process, like what's generated by Hall 4, right?
So this is what I was saying. So firstly, like the proofs actually are very detailed, and the proofs, like those 16,000 lines of script, if you want to actually verify them, you will need to read like probably 500 megabytes of steps, which is impossible. But the way you guarantee, like this, the guarantees come from that Hall 4 has a very small trusted code base, which is a few hundred lines, and everything else is built on top of it in a formally verified to be correct. And those few hundred lines of code are like Roman Milner wrote them in the 70s. So they're very, like, no one is suspicious about them. But there are people who actually are trying to verify Hall 4, like to verify Hall 4 within Hall 4. But this is a different topic. But it's a hot topic actually, this whole self-referential verification.
So I have a question actually about the bounds and not about the theorem proving.
Yeah, sure.
So what you described kind of provides an upper bound for a problem, but not for a specific state, right? But can you use kind of snapshots from a given state to give an upper bound on a length of a plan from that state?
Yes. Yeah. Given that the state space is acyclic, yes, or yes, this is the main condition. So yes, if the state space is cyclic, then you can do that.
Okay.
Yeah, and you can also use it. Like I didn't do that, but I mean, you can also use it if you have. You can also like instead of using the snapshots to compute upper bounds, you can probably just compute plans within like compute one plan for the acyclic part of the state space or and then within each and this will be easier because the acyclic state part of the state space is very small. It's a projection. And then within each snapshot, compute a small plan that reaches from one state to the next one. Yeah.
Do you have some per domain data, like where these new bounds have to improve performance? Like, do you have a slide per domain results?
No, unfortunately, no. But in the paper, there are there's a detailed how many instances of which domains were proven unsolvable.
All right, so we're out of time. So let's thank the speaker again.